We'll explore how climate factors directly shape the design of dense urban environments around the world. Each city example we'll discuss, Masdar City, Singapore, and Freiburg-Vauban, represents a unique response to its specific climate challenges, but they all share a common approach: using climate as a foundation for design rather than a limitation. Through these case studies, we can see how urban form, orientation, and environmental logic work together to create comfortable and efficient spaces. Masdar City shows how compact form and wind management respond to a hot arid desert climate. Singapore demonstrates how natural ventilation, shading, and greenery address a hot humid tropical context. And Freiburg-Vauban illustrates how solar planning and passive design optimize a temperate European environment. Together, these examples highlight that climate-responsive design is not about a single solution. It's about adapting form, orientation, and technology to fit the environmental logic of place. They demonstrate that sustainable density is possible anywhere, when climate becomes a creative force in the design process. Masdar City in Abu Dhabi represents one of the most ambitious attempts to design an urban district entirely around climate logic. Located in a hot arid desert environment where summer temperatures exceed 45 degrees Celsius, the project was conceived as a low-carbon, high-density prototype city. What makes Masdar significant is not only its technological ambition, but its return to traditional environmental wisdom. Instead of fighting the desert climate with energy-intensive systems, the master plan reinterprets vernacular Middle Eastern strategies, such as compact form, shading, and wind capture, through contemporary materials and engineering. In this sense, Masdar is not simply a green city, but a spatial experiment demonstrating how urban density can become a climatic tool. It asks a critical question: can form, orientation, and spatial configuration reduce energy demand before technology is even applied? The compact urban layout of Masdar is fundamental to its environmental performance. In hot arid climates, dispersed development increases solar exposure and surface heat accumulation. Masdar instead adopts a dense, inward-oriented fabric composed of narrow streets and closely spaced buildings. Street orientation is carefully calibrated to capture prevailing northwesterly winds while minimizing exposure to harsh southern and western sun angles. The height-to-width ratio of the streets ensures extended shading throughout the day, dramatically lowering ground temperatures compared to open desert surroundings. This creates a walkable environment even under extreme climatic conditions. Density here is not accidental, it is strategic. By reducing exposed surface area and increasing self-shading, the urban form itself becomes a passive cooling mechanism. This challenges the assumption that density automatically generates heat stress. Instead, intelligently designed density can moderate it. One of Masdar City's most iconic elements is its contemporary wind tower, inspired by traditional Gulf, bargeal, systems. Rising 45 meters above ground, the tower captures cooler air at higher altitudes and directs it downward into public courtyards. This passive ventilation system enhances air circulation at pedestrian level, reducing perceived temperatures. However, the tower functions effectively because it is integrated into a compact urban fabric. Narrow streets accelerate airflow through pressure differentials, while shaded plazas prevent excessive thermal buildup. In other words, ventilation is not dependent on a single object but on the relationship between architecture and urban density. The reinterpretation of vernacular climate knowledge demonstrates that sustainability is not only technological innovation but also cultural continuity. Masdar shows how traditional environmental intelligence can be scaled to contemporary urbanism. Courtyards in Masdar operate as microclimatic moderators within the dense fabric. During the day, shaded surfaces absorb heat more slowly than exposed desert ground, while vegetation and water features promote evaporative cooling. At night, stored heat dissipates gradually, stabilizing temperature fluctuations. These semi-enclosed spaces also facilitate vertical air movement. Warm air rises while cooler air circulates at pedestrian level. Beyond environmental performance, courtyards act as social anchors, reinforcing community interaction in shaded, thermally comfortable spaces. This dual function, climatic and social, reflects a core principle of sustainable urbanism: Environmental performance should enhance, not compromise, social life. Masdar's courtyards therefore illustrate how density, when spatially articulated through voids and shaded centers, can generate localized climatic comfort in extreme conditions. In hot arid regions, solar radiation is the primary source of heat gain. Masdar's building envelopes are therefore designed as environmental filters. Shading screens, perforated panels, and recessed windows reduce direct radiation while allowing controlled daylight penetration. High-performance insulation and reflective materials further limit heat transfer. Rooftop photovoltaic arrays generate renewable energy, integrating active systems with passive form-based strategies. Importantly, the facades are not merely aesthetic gestures, they function as climatic mediators. By reducing cooling loads at the building scale, they reinforce the performance of the overall urban system. The city demonstrates how architectural detail and urban planning must operate together to achieve low-energy outcomes. Masdar City ultimately demonstrates that urban density can serve as a climatic infrastructure. Compact form, passive cooling, renewable energy, and traditional environmental logic are not separate strategies, they operate as an integrated system. The project remains experimental and not without criticism, yet its conceptual contribution is significant. It reframes density as an opportunity for climate adaptation rather than a liability. For hot arid regions facing rapid urbanization, Masdar offers a prototype suggesting that environmental logic must shape form from the earliest planning stages. Singapore presents a very different climatic challenge. Unlike the dry desert of Abu Dhabi, Singapore experiences a hot humid tropical climate characterized by high temperatures, intense rainfall, and persistent humidity. In such conditions, the primary design goal is not retaining warmth but enabling ventilation and managing moisture. Despite its extreme land scarcity and high population density, Singapore has positioned itself as a global model of green urbanism. The city demonstrates that vertical growth and ecological sensitivity can coexist. Rather than treating density as a thermal burden, planners have transformed it into a framework for integrating vegetation, airflow, and water management systems. Singapore asks another critical question. How can high-rise density remain breathable in a humid climate? Singapore's dense urban form is carefully structured around transit-oriented development, minimizing sprawl and reducing transportation emissions. However, density in tropical climates risks trapping heat and obstructing airflow. To counter this, the city preserves ventilation corridors aligned with prevailing wind directions. Street canyons are proportioned to balance shading and air movement. Urban greenery functions as a thermal buffer between building masses, reducing surface temperatures and mitigating urban heat island effects. Thus, density becomes calibrated rather than excessive. The built form is intentionally porous, allowing the city to breathe. This demonstrates that compactness must be accompanied by strategic openness. A defining feature of Singapore is its network of shaded pedestrian pathways and park connectors. These green corridors link residential districts to commercial centers and nature reserves. Vegetation-lined routes provide evaporative cooling and shade, significantly improving pedestrian comfort. In a tropical environment where exposure to direct sun can be overwhelming, these pathways transform mobility into a climate-adapted experience. By prioritizing walking and public transport over private vehicles, Singapore reduces heat-generating traffic congestion. Here, infrastructure serves both ecological and social purposes. Mobility planning becomes climate planning. Many of Singapore's residential towers incorporate void decks, sky gardens, and naturally ventilated atriums. Buildings are oriented to capture prevailing winds, and their massing allows air to flow between and through structures. This reduces dependency on air conditioning, a major energy consumer in humid climates. Vertical courtyards and open communal spaces promote cross-ventilation even at elevated levels. In this way, high-rise density does not eliminate natural airflow. It reorganizes it vertically. Singapore's approach illustrates how climate-responsive design must extend beyond the ground plane into three-dimensional urban space. Solar gain control is essential in equatorial regions. Buildings employ horizontal overhangs, louvers, and double-skin facades to filter intense sunlight. One of Singapore's signature strategies is vertical greenery, green walls and planted terraces that provide shading and insulation while enhancing biodiversity. Reflective materials and cool roofs reduce heat absorption. These facade systems combine passive shading with ecological integration, demonstrating that architecture can function as environmental infrastructure. In Singapore, greenery is not decorative, it is performative. Singapore proves that density and sustainability are not mutually exclusive. Through long-term policy alignment and climate-aware design, the city has embedded environmental logic into every scale, from regional planning to facade articulation. In tropical climates especially, airflow, shading, and vegetation are not optional enhancements but structural necessities. Singapore's model suggests that future megacities must design for breathability as much as for efficiency. Vauban, located in Freiburg in southern Germany, is widely recognized as one of Europe's most successful eco-districts. Developed on the site of a former French military base in the 1990s, the district was conceived as a model for low-energy, community-oriented urban living. Unlike extreme climates where survival strategies dominate design, Vauban operates within a mild temperate climate, with cold winters, moderate summers, and balanced seasonal variation. Here, the key environmental challenge is reducing heating demand while maximizing solar gain. What makes Vauban particularly significant is the integration of density, solar orientation, and citizen participation. The project was shaped not only by planners and architects but also by cooperative housing groups. As a result, sustainability in Vauban is not purely technical, it is social and spatial. The district demonstrates how climate-responsive planning can support both environmental performance and collective urban life. In Vauban, density is deliberately structured to enhance energy efficiency. The neighborhood follows a compact, mixed-use model that integrates housing, schools, shops, and services within walking distance. This reduces transportation energy demand and supports daily life without car dependency. Streets are designed primarily for pedestrians and cyclists, while cars are limited or kept at the perimeter. This car-reduced strategy significantly lowers emissions and noise pollution. At the same time, building blocks are carefully arranged to minimize heat loss. Compactness reduces exposed facade surface area, which is particularly important in winter conditions. Central green spaces and courtyards ensure daylight access while maintaining a cohesive urban fabric. Therefore, density in Vauban is not overcrowding, it is calibrated compactness. The urban form balances energy logic with human scale, reinforcing both environmental and social sustainability. One of the most defining principles of Vauban is its strict solar orientation strategy. Planning began with detailed sun path analysis to optimize winter solar gain. Nearly all residential buildings are oriented southward, ensuring maximum exposure to low winter sun angles. Building spacing is carefully calculated to prevent overshadowing between blocks, especially during colder months when passive solar heating is most valuable. This orientation reduces reliance on mechanical heating systems and enhances indoor comfort naturally. Furthermore, the consistent alignment of roofs allows efficient installation of photovoltaic and solar thermal panels. In this sense, urban form and renewable energy infrastructure are inseparable. The city layout itself becomes an energy-generating framework. Vauban demonstrates how climate data, such as sun angles and seasonal variation, can directly shape the geometry of streets and buildings. Here, environmental logic precedes architectural expression. Vauban is internationally known for its concentration of passive house buildings, structures designed to require extremely low heating energy. These buildings achieve performance through high levels of insulation, triple glazed windows, airtight construction, and heat recovery ventilation systems. As a result, indoor temperatures remain stable even during cold winters with minimal mechanical input. Many housing units produce as much energy as they consume, and some even generate surplus energy through rooftop solar panels. In addition, the district is connected to a local biomass-based district heating system, further reducing fossil fuel dependency. What is remarkable is that these passive design principles are not isolated pilot projects, they define the entire neighborhood. Vauban proves that ultra-low energy standards can operate at district scale, transforming sustainability from individual buildings into a collective urban strategy. Environmental design in Vauban extends beyond architecture into landscape and ecological systems. Tree-lined streets provide seasonal shading, allowing sunlight penetration in winter while offering cooling in summer. Green roofs and permeable surfaces reduce stormwater runoff and mitigate flood risk. Rain gardens and bioswales naturally filter and absorb rainwater, minimizing pressure on drainage systems. Shared courtyards with vegetation support biodiversity while functioning as social gathering spaces. These green networks also contribute to microclimatic moderation, reducing localized heat accumulation and improving air quality. Importantly, ecological systems are visible and integrated into daily life, reinforcing environmental awareness among residents. Vauban operates not only as a residential district but as a functioning ecological system. This integration of infrastructure, landscape, and community strengthens long-term resilience. Vauban demonstrates that climate-responsive design is not exclusive to extreme climates. In temperate regions, the key challenge lies in optimizing solar gain, minimizing heat loss, and balancing seasonal variation. Through compact density, strict solar orientation, passive housing standards, sustainable mobility, and green infrastructure, Vauban achieves substantial carbon reduction while maintaining high quality of life. What makes it especially powerful is its community-driven development model, which aligns environmental performance with social cohesion. The district illustrates that sustainability is most effective when spatial planning, energy systems, and citizen participation converge. Freiburg-Vauban therefore stands as a replicable model for temperate climate urbanism, proving that thoughtful density, informed by climate data, can generate both efficiency and livability. When we compare these three models, it's clear that climate is not a limitation but a design driver. In Masdar City, urban density and orientation combat extreme heat through shade, wind, and solar control, a perfect example of adapting compact form to a hot arid environment. In Singapore, density coexists with lush greenery and ventilation, showing how a humid tropical city can breathe, cool, and thrive vertically while staying livable and walkable. And in Freiburg-Vauban, solar-oriented design, passive houses, and green infrastructure prove that even temperate cities can optimize density for environmental and social performance. Each represents a unique response to local climate, but together they reveal one universal principle. Sustainable urban density is achieved through the intelligent integration of form, orientation, and environment. Urban form gives structure to our cities. Orientation determines how we respond to sunlight and wind, and environmental logic connects design with ecology. Passive environmental design then translates these principles into practical architectural performance. From hot deserts to humid tropics to temperate Europe, Masdar City, Singapore, and Freiburg-Vauban each show that climate-responsive design can take many forms, but all aim for the same harmony between density, comfort, and sustainability. In the end, true sustainable design isn't only technical, it's about understanding the dialogue between people, place, and climate.